Okay, thank you for this introduction, and thank you, everybody, to listen carefully to this last talk of this session. So as you may see, the title of my talk has a little bit changed. As in the first part, I would like to present what will happen and how a superhydrogenated PAH will evolve under VUV irradiation. And I will try to link and connect this with the topic of studying water pH interaction, and especially studying the structure. So let's start with a bit of context, and as it has been shown during the last talks, pH and astro-pH may exist in some photodissociation region. They absorb UV light, they emit in the infrared, and among the data that are observed, some bonds are coming up, aromatic bond and aliphatic, and people want to assign this bond to some pH derivative. Some good candidates for them are alkylated or superhydrogenated pH. And basically, what we want to do and what we want to ask at first is, are these pH or are these molecules living there, and how do they evolve when they are irradiated by VUV light? Are they destroyed or do they survive? So how do we do that? In principle, we want to isolate the pH. In our case, it will be cations in an astrophysical relevant environment to shine light on them, and then to study their the process are ongoing, like statistical direct fragmentation, radiative cooling, etc. In practice, this is what it looks like. We use a Pyrenea, the Pyrenea setup, which is basically an ion trap, a cold ion trap, where the pressure is sufficiently low, the temperature is sufficiently low to simulate, let's say, relevant astrophysical condition. And how does it work? So we have installed a VUV source on this cryogenic ion trap. We can inject ions that are desorbed and laser desorbed and ionized here. They are staying and isolated in this cold ion trap for a few minutes, and during this time we can irradiate them. The advantage of using this FTICR MS cell is that we can also perform some mass spectrometry, non-destructive one, as a function of the irradiation time. So now we'll just show you a bit the methodology on not a superhydrogenated cation, but it will be the same for the following of my talk. Here it's on methylcoronan, but whatever. So here at we can isolate completely methylcoronan, so without isotopolog, and then we irradiate it for 200 seconds of UV light. I forgot to mention it's at 10.5 EV, and what we see is the appearance of fragmentation channel with a loss of H or C2H2, etc. Of course, we can continue the irradiation, and these species then they fragment at their turn. So by plotting the intensity of each fragment as a function of the VUV irradiation time, we obtain this kinetic graph, where on the top you have the main fragment, on the bottom the lowest fragment. And the idea is then to retrieve the fragmentation map out of these results. To do such, we build a system of differential equation where each line represents the derivative of the ion yield of each fragment and contain some term of population and depopulation. And actually, this system, this master equation, is basically equivalent to a fragmentation map where each fragment is either populated or depopulated. And each arrow here is corresponds to the absorption of one VUV photon. Then we fit our experimental result with this master equation, where only the fragmentation rates are adjusted. By doing such, we can retrieve the fragmentation map with the fragmentation rate, which are scalable with the VUV flux, and we see that it can give some interesting information. I won't detail this because I want to move on the topic of today, which are the superhydrogenated pH. So in the following, there are some maps that has been done in a previous work of superhydrogenated pyrene compared to the map of pyrene alone. The first thing that you can see is that actually the VUV flux here is destroying the backbone of the pyrene, which is losing either C1, C2, or C3 fragment as a first step after irradiation. While for pyrene, we just see mainly a sequential H loss. So in this case, superhydrogenation is actually not protecting, but increase the destruction of the backbone of this molecule. And this was in agreement with what you can find in the literature. But actually, this story of protection or destruction of the backbone started in 2014 with a paper of Reitzma that has shown that actually superhydrogenation seems to protect the PAH molecule, which is then in opposition with what we have seen on pyrene. So we wanted to study that, and we started by this precursor, which is H6-coronen. By using the laser desorption ionization technique, we can see that we can produce all the superhydrogenated coronen that we can then isolate and study as a function of the VUV irradiation time. And this is what we see there. And now we'll present you the fragmentation map of this species independently. So first, the coronen. So it's very simple, just a sequential loss of H with the first step, which is quite very slow, as you can see by the value of the fragmentation map rate, sorry. And for H-coronen and H2-coronen, it's about the same. We have just sequential loss, so it seems to correspond to this protection. Again, for H3 and H4-coronen, we have some loss. Here you can see that the first loss are 2H, which can be H2 or 3H loss. Here you, in H4 coronen, you even see 4H loss, which could be, let's say, 2H2 loss. And then when you increase the superhydrogenation, you start opening a new fragmentation channel, which is a loss of carbon. Here in this case, we have carbon 1 and carbon 2 loss. And for H6 coronen, only carbon 2 loss. So we wanted to explain a bit this in detail. So we did some simulation with some, let's say, molecular dynamics coupled to SSC's DFTB, which is an approximation of the DFT. So we started by H5 coronen with 22 EV inside, and we could see different fragmentation channel, the H loss, which is caused by the shift of an hydrogen on the backbone. We could see some H2 loss, which is caused in this case by migration of one hydrogen on a centered carbon ring. And then we could see some C2H4 loss caused by the motion of hydrogen on carbon inner edge carbon. So and then a double C breaking. By looking at the number of loss as a function of the simulation time, we could see that the two, let's say, carbon loss and H loss are more or less equivalent, they are competing, and but we could retrieve basically what we saw experimentally, at least the channel we saw experimentally. We wanted then to investigate a bit more the role of the isomer. And actually, the simulation I've presented you was the lowest energy isomer. But when going to an isomer which is certainly more probable experimentally, we could see the same kind of loss, more losses actually. And but let's say with a ratio more in favor of what we saw experimentally. So this means that the H or the isomer where the H are different, let's say, on the backbone is important for the fragmentation. So just to summarize this part, we could see that superhydrogenation is actually protecting the coronary backbone up to a number of additional H, which is equal to 4. And we could see that the VUV photoprocessing of this species is releasing H2 and C2, which can be interesting for astrochemical context. Some phenomena to investigate. We can wonder if this phenomena can be extrapolated for larger pH, meaning that for a larger number of carbon atoms, certainly there will be a need of higher number of hydrogen to start breaking this backbone. And then we would like to investigate some isomer effect and the role of H migration. So now I would like to contextualize and let's say to connect this to water pH interaction. And to do such, let's take a very simplified scenario in which water and pH molecule can stick together in colder region of the ISM. And actually, it was shown that if you add VUV on the top of that, you can change and transform the pH by oxidizing it or actually adding some hydrogen. So let's say by moving some hydrogen from the water to the pH. So in this context, I would like to study more in detail the chemical reaction at the quantum level and to see what is the role of H migration. And to study this from a, let's say, molecular physics point of view, I will take the easiest system, which is 1 pH and 1 water, and eventually add some water or pH unit to systematically understand better this kind of effect. To do such, we need a source that produces some pH water cluster. This is a source that has been built in our team, in which we have the pH sample powder, which is evaporated and brought by an helium flux into a double wall cold chamber cooled down by liquid nitrogen. At the end of the oven, we have an electron gun that ionize this pH. And eventually, you can inject some water to have a growth of cluster made of pH and water. And as you can see, the main peak are hydrogenated, in this case, it's pyrene cluster. And zooming on the peak in between, you can add some water molecule. We can use this source in a broader setup, which is made of mass selection to select one of the cluster, kinetic energy focusing tools that will focus in kinetic energy this cluster into this collision cell and fulfill with the different RAR gaze. And the product of this collision will be analyzed by a reflectance time of flight mass spectrometer. So we did some measurement on pyrene with 1 to 4 water molecule. And what we could see is that the fragmentation yield of pyrene with 1 and 2 water molecule starts at the same machine. We are developing this new machine made of the cluster source I've just shown you, connected to a cryogenic quadrupolar ion trap and a TOF-MS, in order to tag this water pH cluster and to study their infrared spectra as a function of their composition. This will be, so the aim of the project, again, will be to study this as a function of the composition in order to link this result to some GWST data and to work with astrophysicists in order to better understand and interpret this spectra. This is all part of also my project, ANR project, which is called CASULEX. So it is run in Toulouse. But in this case, it will mean that we will characterize the spectral signature of astro-relevant carbonaceous cluster experimentally. And in September 2025, we will open a PhD position. So please feel free to contact me if you want to join us and we can discuss. Okay, and with that, I would like to thank all my colleagues from LCAR, IRAP, LCPQ, LCCQS, and the fundings, and I would like to thank you for your attention.